Hello there, and welcome to this collection of notebooks and tutorials on multirate signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and this notebook is about sampling. So basically, this is a repetition of a lecture from another series we have in Advanced Digital Signal Processing. And there I recommend you to check the lecture number 6, that we also talk about sampling, but we go more in depth into certain topics. And here we give a general overview, and we also include an example in the end, and we'll use concepts from the previous tutorial, and we use filters and Kaiser windows and things like this. So let's get started. In this example, we'll just create an audio signal in Python, and then we will filter it with our previous low-pass filter that we use the Kaiser window with beta equals to 8. So here I'm just importing some libraries. I'm going to use matplotlib and numpy and scipy signal. I decided not to use librosa this time because instead of using music, I'm creating a signal with some tones. So we have this fundamental frequency of 220 Hertz, and then I'm doing just some fade in, fade out, so our signal is a bit smoother. And then I'm just adding some harmonics in high frequencies, and this is how our signal sounds. Well, when we look at its frequency spectrum, we see that we have our frequency of 220 Hertz here, and then we have all these frequencies here above 8 kilohertz. So we are using 32 kilohertz of sampling frequency, so our Nyquist frequency is 16 kilohertz, and it would be equals to pi, and half pi would be approximately 8 kilohertz. So we have all these frequencies over 8 kilohertz. So we will low pass it, and we will take our Kaiser window, low pass design, length equals to 32, and it's the same what we did in previous tutorial. And here now we have our filtered signal. So for example, if we're doing downsampling when n is equal to 2, so we would have up to 8 kilohertz, and we would like to filter out everything above 8 kilohertz. So maybe we could use this filter, and we see that we have indeed above the half pi, everything is attenuated. So we observe that the beginning frequency 1.5 we have indeed much attenuation, and we can listen. So this is the original with the high frequency components, and here is the low pass version. And now we can downsample it by a factor of n equals to 2, including the removal of zeros. So this is what we are doing here. We are downsampling by a factor of 2, and this is the frequency response. So observe that now we obtain a stretched spectrum. So this part here is very similar to this part here, and we can listen to this downsampled. We see it's muffled, it's the same, but now at half the sampling rate. If we want to upsample it again, we can use this indexing trick, and now just on the receiving side we are effectively inserting a 0 after each sample. So observe that in this way we can avoid the function downsampling or upsample, which makes it clear to see and check what happens. So here now we have the upsampled version of our signal, and now we have the shrinking and periodic continuation of the spectrum. So we have this aliasing components at high frequencies. So this was the low pass version, downsampled. Now we upsample by inserting zeros, and we have this here, so we have all these aliasing components. So this part is effectively this part here, so we have the shrinking, and we can listen. It's difficult to hear aliasing here because with my headphones or with my computer speaking, it's very hard to reproduce these high frequencies, but the aliasing components are here and we must get rid of them. So we will low pass this result. So now we will low pass again using the same filter, and this is the frequency response. We're using signal, SciPy signal frac Z. We're convolving with the filter, doing the same what we did. And observe that now we remove the aliasing component at high frequencies, and when we listen, sound the same as the lower sampling rate, but now at the higher sampling rate of 32 kilohertz. Sometimes, if you use different audio signal to test, you'll find that there could be differences due to not sufficiently attenuated aliasing.